Hello dear students, welcome you all. So in this lecture I am going to discuss about the all pass filters, right? All pass. This is the last, type of filter that we have discussed in this course. We have discussed right from the low pass, then high pass, then band pass, then band reject, and now we have arrived at a all pass filter. So what is a all pass filter? First of all, we have to understand all pass filter is that type of filter in which all the frequencies that are present in the input signal, they are going to be present in the output signal, right? It is going to pass all the frequencies that are present in the input signal. So why we are calling it as a filter, right? So we call it as a filter because it is actually doing the process of phase corrections. How it is doing the process? This is very important property of this type of filter, that it induces a phase difference between the input frequencies and output frequencies. Clear? So this is very important parameter. Although it don't attenuate or suppress any frequency, but it create a phase difference between the input and output for the different frequencies, right? So this is a very important parameter of property of this type of filter. So when we send a signal from one place to another place, there can be a distortion in the signal that results in the phase alteration of that signal, right? I mean, the phase of that signal is shifted. So we can use this filter for correcting that phase, right? So all pass filters are also called as phase correctors, right? Or even in phase modulation, we can use this type of filter for inducing a phase, right, between the input frequency and output frequency of a signal, right? So it has a wide range of applications in all electronic applications, right? It is doing the same process as the other filters are doing, just it has a difference in as it do it in case of a phase. Clear? If we want to create a shift in the phase, we can use this filter. If we want to correct the phase a distortion in any signal, then we can use this type of filter. So this is the application of this filter. So now we will see the circuit diagram of this type of filter. So this circuit diagram consists of basic operational amplifier, right? This is operational amplifier. This is output terminal of operational amplifier. This is the first terminal, inverting terminal, right? Right. Here you can have it, load resistor here, right? Now you can have this here. This is the second terminal here, right? This is the space for capacitor connected here, This is for the input signal. Right. So now I'm going to add all the circuit elements here in this circuit. So it is resistance R1, it is feedback resistor RF, but here we have taken it equal to R1. This is load resistor RL. This is here B output. This is virtual ground. Clear? This is plus, this is minus. Again, we have a resistance here. This is R. This is the capacitor, and this is a input signal. You can have, right, B input, right. This is again the ground, virtual ground here. So here you will have a capacitor. This is C. Again it is virtual ground. Clear? So now we are left with only the supply voltage for the operational amplifier, right? So it is plus BCC, it is minus BEE, right? Gain of this basic amplifier A. Now you can see this circuit. This circuit has two sections. This is the first node 1. This is the second node 2. Yeah. This is feedback path. Right. Now you can see here this is the circuit diagram for a all pass filter. Right. Now if I look at the output, what I said earlier, then we can draw the output of this waveform here. Right. So this is the output voltage. Clear? B output. It is for a frequency. Clear? So if you look at the output signal, suppose this is the input signal. This was the input signal. Clear? I have taken a very simple kind of signal. Then in case of this filter, whatever output we will get, that will be, you know, right. So you can see here that there is a difference between the phase difference between the V, this is V input signal, and this is V output. So you can see there is a definitely phase difference of angle phi between the input and output. So this is the difference that circuit induced between the input and output. Clear? If we have different frequencies, then obviously it will create phase difference between the all signals, all frequencies. So we have took a case of one signal here. So you can see it is going to induce a phase difference here, right? You can see the phase diagram. Now I'm going to write down the expression for the output voltage. Clear? So to find the expression for output, we will use principle of superposition. This principle of superposition states that in case of this amplifier, the B output will be equal to the sum of the inputs, these two inputs, right, separately. But the condition here is that when we are finding the output due to this part, in that case, this will be at ground And when you are finding the output due to this part, then this will be section will be at ground. So we will start from the first part. Clear? I can say B output is equal to B output 1 dash plus B output 2 dash. This is the principle of superposition in case of operational amplifiers. Right. So first of all, I am going to use take this output due to this input. So for it, let's take here that we have grounded this now. Clear? So when you grounded this, now we are left with only this circuit. Clear? So that is it is B output 2 dash. So we know in this case now it is operational amplifier working in inverting mode. So B output is equal to what? Minus R1 upon RF. Clear? Into B input. We have learned it from in the theory of operational amplifiers. So here as R1 and RF are equal, so simply B output is equal to negative V input. Negative sign is here because we are using inverting terminal of the operational amplifier. Right. Now this is the first thing that we did. We completed B output 2 dash. Clear? This is the output due to this input. Now I am coming to the second one. When I am coming to the second one, then now we will ground it. Clear? We will ground it. Clear? We will have this circuit here. Clear? So right. So now we will have B input here. Here it is at now ground, and B input is now at this terminal. Clear? Because initially B input was common to both, and this is resistor. Even I can take it in much better way. This is now R resistor. This is capacitor C, and this is the virtual ground. Now you can see at this circuit, what is this? You might have remembered this circuit. We have already discussed this circuit, and this is what? This is low pass filter. Clear? We have discussed it already. It is a low pass filter, right? We have found the expression for the output of a low pass filter earlier. So it is now it is this output will be due to this one, right? First node, and it is B01 dash is equal to minus 2 iota XC upon R minus iota XC B in. This is the B output 1 dash. This is because of this input, right? We have already calculated it. So now we are going to put the value of these to V output 1 dash and B output 2 dash in this equation. So what you will get? You will get it is B output is equal to minus 2 iota XC upon R minus iota XC B in. Clear? Second was minus V in. Clear? We have calculated it here, right? So now we have put the values of this one and this one. This one is because of this voltage, this signal appearing at node A. We have already calculated it. For your convenience, I can recall it. It was, B output was, when we have discussed low pass filters, it was equal to 1 plus RF upon R1 into B A. If A was the voltage at this node. Yeah, I can say it is B1. Clear? So when you put the value of B1, it becomes 1 plus RF is equal to R11. When you put the value of B1, it was minus iota XC upon R minus iota XC. So when you into B in. Clear? So when you put this value here, after simplification, it becomes 2 iota minus iota XC divided by right. So the things are very clear here. Now we have this expression, B output is equal to this. So when you will simplify it, we'll put the value of XC, right? What is XC? It is 1 upon 2 pi FC, capacitive reactance. Clear? We have done all these things in the case of low pass filters. So when you will simplify, you will get B output upon B input is equal to 1 plus 1 minus 2 pi iota RFC upon 1 plus 2 pi iota RFC. So this is the expression that we got after simplifying this and putting the value of this. You can do it. So when you will take the magnitude of it, you can see magnitude of numerator plus divided by magnitude of denominator. 1 plus 2 pi RFC square, right, divided by 1 plus 2 pi RFC. FC square whole term under the root. This is the magnitude. So it got cancelled. Clear? So you got B output upon B input magnitude is equal to 1. Right. So as I told you in the beginning, that in this case, whatever the intensity of the input signal, the same intensity will appear at the output. There is no attenuation of any frequency, stoppage of any frequency. So B output is equal to magnitude B input, right? So this was the output of this all pass filter. But look at the phase angle, right? So if we look at the phase angle phi, then phi is equal to tan inverse by upon x. We know it from the mathematics of complex numbers. If we have a complex number, zeta is equal to x plus iota y, then you can write it in this way. Now you have 2 in the numerator and in the denominator. So we will write it for both. Tan inverse, here what is y? Minus 2 pi iota RFC. And what is x? It is 1. Similarly, in denominator, this is the rule of complex numbers. Tan inverse, it is 2 pi iota RFC divided by 1. Because here x is 1, this is x and this is y. This is x and this is y. Sorry, I have used iota here. Iota will not be used when B took the complex form, right? This only tan inverse minus 2 pi RFC upon this. This is the phase angle. Clear? But we took the phase angle for the numerator and for the denominator. The ratio is the phase angle. Clear? Then when you simplify it in the knowledge of complex number, it will become tan inverse minus 2 pi RFC. It will go in the upside, then it will become negative. Tan inverse 2 pi RFC. Now tan inverse negative of theta means minus tan inverse theta. So it becomes like this. Clear? So in the next step, you can have this equation. So when you simplify it, you got tan inverse phi is equal to minus 2 tan inverse 2 pi r f c. So this is the phase angle, clear, phase difference that is induced between the input frequency and output frequency. And you can see here that it is frequency dependent. It depend upon the frequency, it depend upon the value of capacitance, resistance, right? But the main thing is resistance and capacitance are fixed in the circuit, clear, but the frequency of the signals that are applied at the input that can change. Even in the input signal there can be different frequencies. So in that case the phase angle will be induced for all the frequencies depending upon their value. So we will have a phase shift for the different frequencies. So what I told you in the beginning, that in the practical applications where we use this all pass filters, we have a range of frequencies or lot of frequencies. So when we want to add some phase angle to those frequencies, we can use this filter. If we want to remove the unwanted distortion in the phase, we want to correct the phase of the different frequencies, then we can use this circuit. We can induce the desired phase difference between the input frequency and the output, although the gain is equal to 1 in magnitude, right? It means V output is equal to V input. What very important thing is phase is not same. There is a phase difference between the input frequency and output frequency, right? So this is all about this all pass filter, right? What we did, we took the circuit diagram, then we applied the principle of superposition. First of all, we consider only one input and we found the output, then we consider the second input, then we found the output, then we took the sum of both these by applying the principle of superposition in case of operational amplifiers, right? So thank you very much.